T is said to be 1-to-1, is 1-to-1 or injective. It is 1-to-1 or injective. It is 1-to-1 or injective if for every vectors v1 and v2 in a V, every vectors v1 and v2 in V, such that v1 is equal to v2, then this when vectors v1 and v2 in V such that T v1 is equal to T v2, then this should imply that v1 is equal to v2. So what does this definition say? If you have two vectors in V and they are equal, their images should also be equal. If two objects are equal, then their images, that is the intuition. Two objects are equal, then their images should as well be equal. Then also, saying that a map is 1-to-1 is the same thing as saying that it is injective. Also, one can view that condition as alternatively for all v1 and v2 in V such that v1 is different from v2 for any vectors v1 and v2 in V such that v1 is different from v2, then tv1 should also be different from tv2. In principle, if two objects are different, then their images should as well be different. I want to take that off. I am writing another app, so hope it will not. Don't save. So they are going to be disappearing. So before you remove a particular page, you please tell me. Otherwise, according to the app which I am using right now, if I create another page, the one before will disappear and I cannot cover it back. Then another definition, let T still be a linear transformation. If T is a linear transformation, then we say that T is singular. T is singular. T is singular if there exists. T is singular if there exists this is a linear transformation. A non-zero vector V in V such that TV 0. So the transformation is singular if one can get a vector which is non-zero but is mapped to 0. If you can get a vector which is non-zero but it is being mapped to 0, then we say that our transformation is singular. Then similarly, T is non-singular if there exists no and 0 exists no and 0 vector. Exists no and 0 vector in V. That is mapped to 0. The transformation is non-singular if there exists no non-zero vector that is mapped to 0. Yeah. However, it is singular if one can identify a vector which is not 0 but taken to 0. Now, in principle, a transformation is non-singular if there is a possibility of something getting mapped to 0. If there is a possibility of something getting mapped to 0, then that thing should be 0. In principle, this is what I'm meaning. In particular, for a non-singular transformation, if the transformation, if there is a vector which is mapped to 0, particular TV is equal to 0, if and only if V is 0. Yeah. The only case where the transformation can map something to a 0, that thing should be a 0. Yeah. However, we don't have a non-zero vector being taken for a non-singular transformation. The theorem which I'm going to state here, I don't know whether I should prove it. Okay, I think I should do. I should prove this. Then the next one I will not prove it because this is essential. So the theorem states that let T be a linear transformation. To be a linear transformation, then T is 1-to-1. T is 1-to-1. T is 1-to-1. Or, yeah, I think I should wrap it up here. That's how I should operate instead of having it. So T is 1-to-1 or injective. 1-to-1 or injective. Depend only if kernel of T is 0.